We humans, we like to have things, everything under control if possible. That means predicting everything, how it is going to behave. Or in other words, forecasting it. Be it weather, be it economic forecasting, be it how traffic is going to behave or when the traffic jam will happen. We like everything under control.
But some things are not as straightforward as it looks. We have always thought of prediction as a linear thing, means that the cause and effect are directly proportional. A gentle push to a ball will only move the ball that gently. But that is not always the case. Weather prediction is as old as humans themselves. Ancient people with lack of any tools like thermometer or barometer would observe the sky, animal behavior, and make a prediction. For instance, if they noticed clouds gathering, they would predict a rain in near future. For a long time, scientists believed that given enough data about atmosphere like temperature, wind speed, and pressure, predicting the weather should be straightforward.
Short-term weather prediction was working fine with intuition, experience, and help of some basic tools like thermometers and barometers. One could easily predict if it is going to rain in a couple of hours or next day. It was the long-term forecast that was pretty difficult. Like, will it rain in next month? Will it rain in next season?
Now, this is the tool that was used for weather forecasting. All you need to take is the wind direction and the reading in barometer at sea level. Over here, if I match it from a local location, the reading is A. And what does A say? It says that the weather is settled fine.
Earlier 20th century, Louis Fry Richardson proposed a very different way to predict weather. He introduced mathematical equations, and what he proposed was to divide the atmosphere into small grids and then calculate with mathematics the fluid dynamics with each grid to predict the weather. As you would know, in those days when computers was not there, this way of predicting weather simply wasn't practical.
A change had to come, and it came in 1950s. This change was from manual calculation to digital calculation. It was led by Princeton University mathematician John von Neumann. He advocated the use of computers to predict the weather.
We computed the trajectory of a shell that took 30 seconds to reach its target. A young woman with a mechanical desk calculator spent 1 or 2 days calculating such a trajectory. The ENIAC computed the trajectory in only 20 seconds, faster than the shell itself traveled.
And his intention was to make weather as a weapon. He wanted it to use against USSR to give North America an upper hand in the Cold War. But till that time, weather prediction was looked as a linear thing. Then, one day in 1961, when Edward Lorenz, while running a weather simulation, Lorenz wanted to recheck a certain portion of his weather model. But instead of starting the program from the beginning, as he didn't want to go through the hum and clattering noise of Royal Magby computer, he started right from the middle. He got the printouts of the earlier simulation and re-entered the data from a midpoint. And here is where it gets interesting. Those numbers were slightly rounded off. Instead of typing all 6 numbers like decimal 506127, he just entered decimal 506. Not his fault, as printouts showed only 3 places after decimal to save the space, although computer's memory kept 6 digits after decimal. Lorenz was well aware of this. He expected his simulation to give him nearly the same result as before. After all, what harm could such a tiny difference make? When he came back later to check on the results, Lorenz was shocked. The new simulation started similarly, but after a while, it went completely in a different direction. The tiny difference that he had entered, just 1,000th part of a number, had grown into massive change in the final outcome. And that's when Lorenz had a huge realization. He figured out that long-term prediction was doomed. Weather systems are incredibly sensitive to even the smallest changes in the starting conditions. So think about it. All sensors giving accurate and high precision data all the time is very difficult. And I'm talking about at least 6 places after decimal to predict the weather for next week. What Lorenz stumbled upon came to be known as butterfly effect. The idea that a tiny change, like a butterfly flapping its wings, could lead to big differences down the road. After seeing this, Lorentz created a set of equations to explain this kind of unpredictable behavior. When he plotted the results of these equations, they made a swirling pattern just like wings of a butterfly, called as Lorentz attractor, showing that even though the system followed specific rules, it never behaved exactly the same way twice, the very basis of prediction. This showed that long-term weather prediction was impossible as it followed non-linearity. A gentle push to the ball can throw the ball miles away from the predicted path. You can say that this butterfly effect is an orderly chaos, an unpredicted pattern. And this nonlinearity is not just with weather. Look at this double pendulum, Lorentz's water model. Even a tiny difference in initial condition will lead to completely different pattern. It's like playing a game whose rules change every time you play. And the same thing is with predicting the flow of traffic. Small changes in traffic, like a single car switching lane or a slight delay at a signal, can lead to large and unpredictable effects down the road. A minor slowdown at one point can ripple through and cause a traffic jam much farther along, even when the road ahead seems clear. If you slightly change the position or speed of few cars, the overall traffic flow can change dramatically over time. And same goes with both economy and stock market. Small changes such as slight shift in consumer behavior, a new policy by government, or even a single influential event can have a large and unpredictable impacts. For example, a small drop in companies' earnings could trigger a massive sell-off, which then spirals into affecting other stocks, investor behaviors, and even broader economic conditions. Now, these systems are sensitive to initial conditions, just like weather and traffic.
You know that 2008 financial market crisis, it also showed chaotic elements. Market predictions failed to account for interactions between the housing market, the banking system, and the global economy, which resulted in global financial meltdown.
The interconnected nature of global economies and stock market means that seemingly minor event in one part of the world could have a cascading effects, leading to unpredictable outcomes or non-linearity. This is why long-term predictions of stock market and economies are incredibly difficult, if not impossible. The more complex an interconnected system, the more likely it is to exhibit chaotic behavior, where small changes lead to big, unexpected results. Economists and financial analysts often use this model to predict trends, but just like weather forecasting or predicting the flow of traffic, these models can only go so far before chaos takes over. So, as much as human wants, some predictions are as good as looking at a crystal ball. Thanks for watching. Hey guys, how did you like this video? Please give it a thumbs up and like, share and subscribe, and I'll see you next time around. Bye bye.